Okay, so in this video, we're going to look at setting up mixture problems in 2 or 3 variables. Now, for this discussion, we're not going to actually solve the problems. We're just going to set them up. The solution techniques we will deal with at another time. But the solution techniques, there are many. And so but the difficulty that students often encounter is like getting to the point where they have equations that they can then apply those multiple different techniques to. So this is just going to focus on creating the equations that we need in order to then further solve the problem. Now, there are lots of different kinds of problems that can fall into this category that broadly is similar to mixture problems. So typically we have situations where we have quantities multiplied by weights that are different for each type of thing. So these may involve like dollar amounts. So if we're counting coins, we have dimes and quarters and nickels, and they're equal to a certain amount of money. The weights would be the value of the coin, and the quantity would be the number of coins. We can mix coffee blends, for instance, or we can mix quantities of pure water and saline, or there are different kinds of mixture problems we can use. Financial problems at different interest rates are also sort of fall into the same category. Now, there are two sort of main ways that these problems are described. So in the 2 variable case, we have something like quantity times a weight, and then a second quantity times a second weight is equal to some sort of average quantity, average weight, times a total quantity. Alternatively, you can have this left side of the equation be the same, but then you're only given a total, where you're not given the actual quantity at all, but you're just given what the result of this product is. And so your first equation is going to be one of these 2 types in the 2 variable case. And then the second equation will be of the form quantity 1 plus quantity 2 is equal to some total quantity. So typically they'll tell you like how many coins there are or something like that. Now, the 3 variable cases will tend to be very similar. They will just have a third quantity times weight. And the quantity equation will have quantity 1, quantity 2, and quantity 3. And then you will have to come up with a third equation, either from the problem or some other relationship that the problem describes. Because if you have 2 variables, you need 2 equations. But if you have 3 variables, you need 3 equations. Sometimes that third equation will also be of this form, and sometimes it will just be some relationship they told you in the problem. Maybe quantity 1 is 3 times as much as quantity 2 or something like that. All right, so let's look at an example. So percent solutions tend to be examples of these mixture problems. So in this case, a researcher is working on a flu vaccine and needs to mix 10% sodium iodine solution with a 60% sodium iodine solution to obtain 100 milliliters of a 30% sodium iodine solution. How many milliliters of each solution should be used? So always define your variables. It will make much more sense later when you try to explain what the equation is doing. So here we're going to let X be the quantity of the 10% solution, and Y is the quantity of the 60% solution. Those are the 2 things we're mixing together. What we know is that when we mix these things together, we want to end up with 100 milliliters. So X plus Y is 100. That's our equation number 1. That's that quantity equation. Now, when we get the mixture equation, this is the form quantity total times weight total. I called it price here, but because price is often a thing, but weight total, the average that we want in the end. So here we're going to have X times the weight, so that 10% solution is the weight here, plus Y times the weight of that solution is going to be equal to the total quantity times the percent solution we want for that final quantity. And so when we multiply these all out, we get this expression, 100 times 0.3 is 30, And so these are the two equations that we want to then solve. Now, depending on what kind of course this is for, this may be a substitution problem, that might be elimination. You might be doing it by graphing. You can solve this with using matrices, whatever techniques that you know are available to solve this problem from this point. Let's look at dual investment problems, because this is another one, but this one tends to give that sort of second type of mixture equation where they just give you the total. So here you have $50,000 to invest, and your investment manager has suggested putting part in bonds and part in stocks to minimize risk. The stocks are expected to pay 15% and the bonds 7%. You want a return, or you're expecting a return of $6,000 a year in additional income. So how much should be placed in each investment? So we know that we have $50,000 to start with. So our total equation, our quantity equation, is x plus y is equal to 50,000. Our weight equation is the quantity in the bonds, that's our x. Again, it's always a good idea to write this out. If x is the amount in bonds, then the amount of interest earned is x times 15%, or 0.15 in decimal form. And if y is the amount of money in stocks, then y times the 7%, or 0.07. And that's equal to 60,000. There's no multiplying we have to do on this side. We don't know what that equivalent interest rate is going to be, although we could calculate it since we know how much our investment was. But they've told us how much money we need to earn, and so we just put the $6,000 there. And so that's going to be our set of equations. Our quantity equation, the two things add up to 50,000, and our interest adds up to 6,000. Theater ticket problems are another type of example if there are two groups of people that pay different amounts for their tickets. So a student theater group has sold 3,150 tickets for their play. Adult tickets were $6, student tickets were $4. They took in 15,600 in receipts. So this is already that second type of equation where they just give you the total. How many of each type of ticket did they sell? So our weight equation, our mixture equation, is if x is the number of adult tickets, then that's x times 6. And if y is the number of student tickets, that's y times 4. That's equal to the total amount of money they made. So that's our equation. And then the quantity equation is just that adult and student tickets added up to 3,150. Coffee mixtures. These will also work for like nut mixtures or chocolate mixtures, or any kind of time that you're mixing together sort of the same sort of item, but with different prices for each of the components. So the store owner wants to make a medium priced coffee house coffee mixture from the combination of an inexpensive brand and a premium brand. The inexpensive brand costs $2.80 per pound and the premium brand $4 per pound. The owner wants to make a mixture of 120 pounds of the house blend and wants the blend to sell for $3.20. So this is that quantity total times price again. That's where the price comes from, but quantity total times the weight type of setup. So if x is the amount of the inexpensive brand, then our equation is x times 280. And if y is the amount of the premium brand, then that piece of that equation is y times $4, 4.00. And the result is 120 pounds at 320. $3.20. And so if you multiply these, you get 380 for the cost of the whole mixture. And that is your mixture equation. And since you're adding up to 120 pounds, the quantity equation is would be x plus y is 120. But instead, they also tell us she wants to use twice as much of the inexpensive brand as the premium brand. And so twice as much of the inexpensive brand as the premium brand. So twice the premium equals the inexpensive one. And so that is our second equation. Now, these, for the 3 variable cases, again, these follow through. You may have that extra third relationship, like similar to this inexpensive and premium example we saw in the previous problem, in addition to the quantity equation, because you need 3 equations for 3 variables. But the only difference in the setup process is that we will have a third quantity and a third weight to add. So let's look at this example. We're creating a mixed nut blend from peanuts, cashews, and macadamia nuts. Peanuts are cheap at $2 per pound. The cashews are a little more expensive at $4 per pound. And the macadamia nuts are arm and a leg priced at $7 per pound. The owner wants to sell the mixture for $5. If she wants to use twice as many peanuts as cashews and make 112 pounds of the mixture, how much of each nut, rounded to the nearest tenth of a pound, because we probably aren't going to get nice whole numbers, should be in the mixture? So again, let's look at our, if X is the number of peanuts, the weight of peanuts, then the cost of each pound of peanuts is $2. Y is the number of cashews, the weight in pounds of cashews, times $4 per pound. And then Z is the pounds for the macadamia nuts, times $7 per pound. And the target is 112 pounds times $5 per pound. And so that's one equation. The second equation that we know is that X plus Y plus Z, all of the peanuts, cashews, and macadamia nuts mixed together have to add up to 112 pounds, because that's what we want to end up with. And then that third relationship, if we want to use twice as many peanuts as cashews, cashews are the smaller quantity, gets multiplied by 2 to equal the peanuts. And so then these are our 3 equations to solve a 3 variable problem. And the examples could be very similar for the tickets example or the investment example, or as I said, you can do things like coins. If you have quarters, nickels, and dimes that you're adding up, the weights would be the price of the coins, and then the variables would be the quantity of those coins.